Hi, my name's Dr. Barry Flannery. I'm the founder and CEO here at Zerotech. Welcome to another episode of XT Tech Talks. Today we're going to be talking about battery cell formats, from cylindrical to pouch to prismatic. What are the reasons you might choose one over another, and what are the advantages and disadvantages of each type? And Zerotech here, we use cylindrical cells, but there's two other important types. So the three types of battery cells are cylindrical cells, like the ones we've shown previously. There's prismatic cells, which are basically big blocky cells. And then there are pouch cells that are quite thin. So a big prismatic block and a pouch cell is a thin, little flexible plastic bag. So cylindrical cells are the ones we use, and we'll talk in more detail for the reasons why we think they make a good solution for our product. Cylindrical cells were invented for a lot of electronics components like cameras and laptops. So the original cells used by Tesla in their Roadster were 18650 battery cells used in the laptop industry. So when we talk about cylindrical cells, you've got 18650, you've got 2170, and then even you've got 4680, bigger cells, but still fundamentally cylindrical. Prismatic cells then are large, blocky cells. The core of the cells in each case are quite similar, but we'll come to them in a second. The pouch cell then is basically internally sheets that are stacked on top of each other into a vacuum-packed pouch that the electrolyte is put into. So the differences between each of these cells are quite significant when it comes to pack engineering. So for example, cylindrical and prismatic are self-supporting. That's very important. It means that the can around the battery cell provides mechanical force onto the internals to keep it in contact, to keep it working. The same with the prismatic. The pouch cell needs external force to push it together, because when the battery is in operation, it wants to expand and contract and swell a little, and what that can do is cause the electrodes to disconnect internally. So you need to apply active force onto pouch cells. You need to design an enclosure that keeps them restrained and contained. Inside of a cylindrical battery cell is something called the jelly roll. The jelly roll is basically, if you have a battery, it's got, in a very simplified case, it's got plus, it's got minus, and it's got a separator in between. So if you took that and a battery, you could actually unwind it out like a sheet of paper. But instead, to make them more energy dense, we roll them up. So inside of this battery cell, if you were to open it up, you would see that there's a spirally wound cell packed in like this into this can inside of here. It sits inside of that. And then they squirt in a bit of electrolyte and they connect on some electrodes that you're able to take the power in and out of the battery cells. Prismatic cells can be done two ways. Prismatics can also be cylindrically wound jelly roll, and then they compress it down and flatten it and squish it so that it looks a little bit more square-like. Or else they can be done that they're cut as individual sheets, and then they're all welded at the end, tab welded, and then placed inside of an enclosure. Pouch cells are virtually always just flat sheets, usually speaking, put together, and each of the tabs at the end are welded together into the assembly. There's pros and cons to doing each different type of battery cell. So prismatic cells, because they're bigger, will have better energy density and better volumetric energy density. Pouch cells will also have good energy density, both volumetric and gravimetric. And then cylindrical cells will end up with a very robust structure, slightly lower energy and volumetric and gravimetric, but they have other advantages that we'll come to in a moment. The big advantages of, for example, a pouch cell versus, and also some types of prismatic cells, is if you've got flat sheets, this enables you to use some different materials than what are used in cylindrical and some types of prismatic. So for example, if you're using the separator here on these cells, the separators in most of the cells we use are plastic and they're flexible. But if you've heard of solid state batteries, that have solid electrolytes or different types of separators, that material is not flexible. And what that means is you can't wind it up. You can't actually put it into a cylindrical cell. So some advanced chemistries are available in pouch format only. Now there are other types of solid state batteries that can be wound up and put into cylindrical cells, or prismatics that are done in a sheet format and not a compressed jelly roll. So that's one consideration to look at. The other big one that's really important in all practical engineering is that safety does become an issue for battery cells, particularly high energy density. So it's really useful to have a metal can around your battery. It provides mechanical strength, it provides heat resistance, it provides thermal runaway protection, and it's a self-supporting structure. Pouches are quite fragile. It's very easy to puncture a pouch, and if it thermally runs away, there's basically nothing to protect it. It's just plastic on the outside, a low temperature plastic that can burn and easily cascade or propagate to another battery cell. So that's one of the risks with pouches compared to other cell formats. Prismatic is a bit better. It's encased in a metal box, but there's quite a lot of energy usually inside of that prismatic. And that's something that I want to consider in terms of the fundamental choice of us building our own battery packs here at Zerotech with cylindrical cells. The amount of energy in a cylindrical cell can be about 18 watt hours for a 2170 battery cell, a cell like this. For a large prismatic, because this is 5 amp hours for the cylindrical cell, prismatics can be 100, 200, 300 amp hours. That means that they can have energies in the kilowatt hours range of energy, much more energy. Likewise with pouches, they vary, but they can be quite big. They could be tens of amp hours, if not even 100 amp hours and above for large pouch cells. This is a lot of energy. So in the event of a thermal runaway in a real battery pack where you've got lots of cylindrical cells packed together or lots of big prismatic cells packed together, or even pouch cells. If you've got large units of energy, and if one of your units of energy fails for whatever reason, it is extremely difficult to contain that energy. No amount of technology is really effective. So our advanced foam, passive propagation resistant design, other fire insulating materials will really struggle to contain kilowatt hours of thermal energy being released into the pack. So that's one consideration for large cell formats, is to make a passive propagation resistant design. So something that doesn't have a domino chain reaction inside of the battery pack. Cylindrical cells are great because they're manageable in terms of that. And also you can easily insulate around them, for example in the Zerotech design, with a structural fire retardant foam. While you can apply foams and barriers to prismatics, it's still a lot of energy in each unit to contain. Pouches again are very challenging. They have a lot of energy, and also they have very little protection around the cell itself. So thermal runaway is a major design constraint and consideration for building battery packs. The next piece is that we've spoken in previous videos of the importance of temperature. So heating and cooling a battery is really, really important because you want to keep it at 25 degrees C. Now the problem with large battery cells is getting the heat in and out. The thermal conduction from the battery, it's a function of the distance inside of the battery and the resistance. So if you've got a really big battery cell and you've got it on a warm plate here or a cold plate to heat it, it's going to heat it in a gradient pattern like this, but you're going to end up with a temperature gradient across the pack that while you're heating the bottom of the cell, it's very hot at the bottom, it's lukewarm in the middle, and it's still cold at the top. Or the flip side is exactly the same if you're trying to cool it down. With the cylindrical cell, because it's physically much smaller, it's much easier to do it here because the gradient on something that's this size versus something that's almost as big as this table is much, much lower. So cooling smaller cells is a lot easier. And also, when it comes to pouch cells, you have a similar type of issue to cool practical cells. So big cells, harder to cool, harder to get the energy in and out of the core, especially when the heat is internally generated, because these internal heating effect results in very strong temperature gradients inside of the cell. So even if you have the best cooling in the world outside of the cell, it takes so long for the heat to be conducted out, because as we described, it's a layered material of conductive material, totally insulating material, conductive material, totally insulating material. And the same applies for cylindrical cells. So with a cylindrical cell, you've got a jelly roll that's winding like this, and it's a wind of conducting material, fully insulating material, and then a further conducting material on the other side. So actually, to cool the side of the cells here might not be the best, because you've got a very high thermal resistance going this way versus going this way. But in all real practical packs, getting the most contact area on the battery cell, and for other pack designs, it is actually in practice better to cool from the side of a cylindrical cell in all real-world applications and real-world examples. With large prismatics, the same applies. You want to try and cool them on all sides as best you can, and also for pouch. You want to cool from the side or potentially from the edge. It's also possible to cool from the tabs or the electrodes coming out of the batteries. It's a bit challenging to do this from a pack design perspective, but that's the highest thermal conductivity, lowest resistance path into the cell, but you don't have very much area, so it's quite a bit harder to do that. The other more practical aspect of building cylindrical packs, for example in the Zerotech case, is that we have much more flexibility. So when you take battery cells, if you put them in series, so each battery here, just to simplify it, is 3.6 volts, roughly speaking. If we put two cells in series, you end up with 3.6, you end up with 7.2 volts across that full pack, or that full assembly of cells. So having small units of energy lets you do lots of voltages. This is very important for the type of markets that Zerotech operates in, where we're making a platform to meet many different markets. We want to be able to offer you lots of voltages and lots of capacities. So if you've got small units of energy, I can have modules that have 6 cells, 12 cells, 18 cells, and so forth. Or if you've only got very large prismatics or pouches, it's a lot less flexible. You're going up in much larger increments of energy, and your voltages will be quite different as well. So there's a lot of advantages for using smaller cells from both a safety perspective, a thermal management perspective, but also a platform scalability perspective. But having said that, there are many applications in the world where large format prismatics, particularly LFP batteries that have lower thermal requirements, higher intrinsic safety in some conditions, they make a great solution for certain markets. Likewise, there's an application for pouches because the cell design enables much lower internal resistances of the cells because of the tab design. This means that a lot of the highest performance power packs for hypercars and VTOL electric aircraft applications are usually pouch cells for these reasons. So there's different applications for different cell types. There's no one cell is better than the other. Cylindrical cells are generally the best all-rounder, and also they generally have lower manufacturing costs because they're intrinsically cylindrical. It lends themselves to high volume production methods. So in general, there's a bit of a divide in the market as to which cell is the best cell format. It's almost a religious divide, but what you'll find in the market is generally the west coast of the US is entirely cylindrical cell based. These would be well-known names like Tesla and Rivian and Lucid. They all use cylindrical cells, usually 2170. They're now moving to 4680, many of them. And a lot of those companies have heritage from the Tesla pack design. And it's largely a good design based on some of the reasons that we've talked about here. In a European context, it's largely speaking a pouch-based design in the automotive manufacturers, also some prismatics as well. And then as you go to China, the other major market, it's dominated by large prismatic LFP and now NMC suppliers, dominated by the well-known major battery manufacturers. So again, there's different technical reasons, there's political reasons, and there's some just philosophical reasons for the different types of cells. It is important, if you are buying a battery pack, to understand which ones are being used, because it does impact performance, it does impact lifetime. So cylindrical cells will have a shorter lifetime than prismatic and pouch cells because of the nature of the electrolytes that can be used in them. But this can be managed, and in general, building a battery pack is very challenging because you have to balance many different requirements, and if you optimize just one, you could compromise the whole system based on safety or performance or cycle life. So it's tricky stuff. That's what we at Zerotech have spent many years perfecting our design to offer the best possible solution for the markets that we operate in. Thanks very much for listening to me on a little overview on the different types of battery cells.